The nearest star to Earth is only 4.2 light-years away. That number sounds manageable. Astronomers call it our cosmic neighbor. Science fiction writers have treated it as humanity's first foothold beyond the solar system, the opening move in a story that ends with the galaxy. But the moment you attempt to actually cross that distance, something quiet and terrible reveals itself. The fastest spacecraft humanity has ever built would require more than 70,000 years to complete the journey. A transmission sent home at the speed of light would take over 4 years to arrive. No resupply mission could ever find you. No rescue vessel could ever reach you in time. The distance is so vast that the word nearest becomes a kind of lie, a story your intuition tells you to protect you from the full weight of what the number actually means. The closest star in the universe is already so far away that the attempt to reach it may be fundamentally incompatible with human life as we understand it. If you want to understand why the nearest star is already the most terrifying destination our species could ever attempt, do me a small favor and hit that like button and subscribe. It genuinely helps this channel grow. Now settle in, make yourself comfortable, and let us begin. Look up at the night sky on a clear evening from somewhere in the southern hemisphere. Find the constellation Centaurus. Somewhere within that ancient arrangement of light sits a star so faint that no human eye has ever seen it without optical aid. It radiates barely 1/20th of 1% of the energy our sun produces. It carries roughly 12% of the sun's mass. Its diameter measures approximately 15% of the sun's width. If you were to swap our sun for this object, the Earth would freeze solid within days, midday would resemble permanent twilight, the oceans would begin to crystallize before the first week ended. This small, struggling ember of a star is Proxima Centauri, and it holds a title that sounds like an open door, but functions like a sealed one. It is the nearest star to our solar system, the closest sun beyond our own, the first conceivable destination for any civilization that dares to dream of reaching another star. That title appears in astronomy textbooks, in science documentaries, in mission proposals, in the imaginations of everyone who has ever looked upward and wondered what it might mean to go there. Nearest. The word arrives gently. It implies something accessible. It whispers that the first step beyond our solar system might actually be a step we could take. But that whisper is not true, not a deliberate deception, something subtler than that, a distortion that our own language produces, because human minds evolved to navigate a small, rocky world and never developed the circuitry to genuinely comprehend what 4.24 light-years means when you try to traverse it. Proxima Centauri was first identified in 1915 by Robert Innes, a Scottish-born astronomer working at the Union Observatory in Johannesburg, South Africa. Innes was examining photographic plates of the southern sky when he noticed a faint star moving across the celestial background at an unusually rapid rate. That motion was the clue. Stars that appear to shift quickly against distant background objects tend to be nearby. For the same reason a bird passing your window seems to move faster than a distant aircraft, even though the aircraft travels far faster, in absolute terms. Innes measured the star's parallax, the tiny apparent shift in its position produced as Earth moves around the Sun, and confirmed it was closer to our solar system than any other known star. He named it Proxima, from the Latin word meaning nearest. The name has persisted for over a century, quietly misleading everyone who encounters it for the first time. Proxima Centauri does not travel alone through space. It belongs to a triple star system. The two primary members, Alpha Centauri A and Alpha Centauri B, orbit one another approximately every 80 years at a separation roughly comparable to the distance between our Sun and the planet Uranus. Both are reasonably similar to our own star. Alpha Centauri A is marginally larger, brighter, and hotter than the Sun. Alpha Centauri B is somewhat smaller, cooler, and dimmer. Together, they form one of the most studied binary systems in the sky, visible to the naked eye as the third brightest star system seen from Earth. Proxima orbits this pair at an extraordinary remove, roughly 13,000 astronomical units away, where 1 astronomical unit equals the distance from Earth to the Sun. At that separation, Proxima requires approximately 550,000 years to complete a single orbit around its two brighter companions. It sits so far from them that for generations, astronomers debated whether it was genuinely bound to the Alpha Centauri system by gravity or merely drifting through the same region of space by coincidence. Modern measurements of its velocity settled the question. Proxima belongs to the family, but it belongs the way a distant relative belongs, connected by the thinnest gravitational thread across a staggering divide. Proxima Centauri is what astronomers classify as an M-type main sequence star, specifically M5, 5V. Red dwarfs of this kind are the most common category of star in the Milky Way, accounting for roughly 70% of all stellar objects. They burn hydrogen so slowly, so efficiently, so conservatively that they can sustain nuclear fusion for trillions of years. Our Sun will exhaust its fuel in approximately 5 billion years. Proxima Centauri will continue burning for perhaps 4 trillion years, long after our Sun has expanded into a red giant and collapsed into a cooling white dwarf, long after the Earth has been swallowed or flung into darkness, long after every structure humanity has ever built has dissolved into dust and memory. Proxima will still be glowing, faintly and stubbornly, in whatever remains of this corner of the galaxy. That extraordinary longevity makes Proxima scientifically fascinating, but it also makes the star deceptive. A star that will outlive almost everything else in the galaxy feels permanent, and permanent things feel patient. They feel like they will wait. But Proxima is not waiting. It is sitting at a distance that needs to be extracted from the comfortable abstraction of light years and converted into numbers that actually register as real. 1 light year is the distance light travels in a single year, moving at approximately 186,000 miles per second. Nothing in the known universe moves faster. Light crosses the gap between Earth and the Moon in about 1.3 seconds. It reaches the Sun in roughly 8 minutes. It passes Neptune in approximately 4 hours. It clears even the most generous boundary of the solar system in less than a day. But it requires 4 years, 3 months, and roughly 1 week to reach Proxima Centauri. 4.24 light years. That translates to approximately 24.9 trillion miles, or around 40.2 trillion kilometers. 24.9 trillion miles. Let that number sit for a moment, because your brain is doing something right now that it does automatically with figures of this magnitude. It is rounding. It is abstracting. It is filing the number under very large and moving forward. Human cognition developed to process distances measured in footsteps, river crossings, the width of a valley. It did not evolve to distinguish in any visceral way between 1 trillion and 24 trillion. Both register as absurdly large. Both feel equally unreal. And that collapse of scale is precisely where the deception takes root. Because 24.9 trillion miles is not simply a large number. It is a number that defeats every comparison you have ever used to make distance feel manageable. Consider this. If you could drive a car at highway speed without ever stopping, without sleeping, without refueling, traveling a straight road from Earth toward Proxima Centauri, the journey would require roughly 44 million years. 44 million years at 65 miles per hour. When that hypothetical car set out, the Indian subcontinent had not yet finished its collision with Asia to raise the Himalayan range. The Mediterranean Sea was in the process of drying out entirely in one of the most dramatic geological events in Earth's history. Apes had not yet diverged from monkeys. The entire arc of primate evolution that eventually produced a species capable of asking questions about the stars would unfold and complete itself before that car reached its destination. The engine would need to run for a span of time more than 2,000 times the length of the entire human story. Or approach it differently. If you laid standard American dollar bills end to end, each measuring 6.14 inches in length, the number of bills required to bridge the gap between Earth and Proxima Centauri would be approximately 257 quadrillion. The total value of all money in circulation on Earth, across every currency converted to dollars, sits at roughly 40 trillion. You would need to multiply every dollar currently in existence by more than 6,000 and still falls short of the paper needed to physically span the distance to the nearest star. The bills themselves would carry a mass exceeding that of a substantial asteroid, and they would stretch across a void so empty that for the overwhelming majority of the journey, no star, no planet, no rock, no molecule would be close enough to be seen. This is what 4.24 light-years becomes when you pull it out of an astronomy textbook and try to hold it in your hands. The distance is not large the way a mountain is large or an ocean is large. Mountains have been climbed, oceans have been crossed. The distance to Proxima Centauri is large in a way that quietly mocks the entire concept of crossing. It sits in the language of astronomy, wearing words like nearest and neighbor and close, while representing a gap so extreme that every vehicle, every road, every vessel humanity has ever constructed becomes irrelevant noise on the scale required. And here is where the psychology of the word nearest does its deepest damage. When a person hears that Proxima Centauri is the nearest star, the mind performs an automatic comparison. Nearest means closer than the alternatives. It means the best available case. It means that whatever difficulty the distance represents, it is the minimum difficulty. That mental framing creates a shadow of hope, a sense that because this is the nearest, it must be somehow within reach. But nearest in interstellar terms carries no resemblance to nearest in any human context. The nearest hospital can save your life because ambulances exist. The nearest airport can connect you to the world because aircraft exist. The nearest star cannot be reached because nothing exists that makes the crossing possible within a human lifetime using any technology that has been built, funded, or demonstrated. The word nearest applies to Proxima Centauri, the way shallowest applies to the deep ocean floor. The Mariana Trench descends to nearly 36,000 feet. If someone told you that the shallowest point of the abyssal plain was only 12,000 feet down, you might feel briefly reassured. 12,000 sounds better than 36,000. But you would still be crushed to powder long before reaching it without a vessel specifically engineered to survive that pressure. The shallowest abyss is still an abyss, and the nearest star is still a star system separated from us by a vacuum so wide and so silent that the journey to cross it turns every unit of human-scale travel into a rounding error. The cruelty deepens further when you learn what actually waits at the destination, because Proxima Centauri is not only a star, it is a star with planets, and at least one of those planets orbits within the habitable zone. In 2016, astronomers using the European Southern Observatory's HARP spectrograph announced the detection of Proxima Centauri b, a planet completing one orbit every 11.2 Earth days at a distance of approximately 4.5 million miles from its star, more than 20 times closer than Earth is to the Sun. Because Proxima is so much dimmer and cooler than our Sun, this tight orbit places the planet squarely within the region where surface temperatures could theoretically permit liquid water. Proxima b carries an estimated minimum mass of roughly 1.05 Earth masses, making it broadly comparable in size and likely composition to our own world. The announcement sent tremors through the scientific community and through the public imagination. An Earth-sized planet in the habitable zone of the nearest star. The phrasing alone felt like an invitation written into the structure of the cosmos itself. Here was a world that might, under the right combination of atmosphere and magnetic field and geological fortune, harbor conditions that life could tolerate. And it was right there, at the nearest star, 4.24 light-years away. But the planet situation is complicated. Proxima Centauri is a flare star. It erupts. In 2019, astronomers detected the most powerful stellar flare ever recorded from Proxima, a burst that caused the star to blaze 14,000 times brighter than normal in ultraviolet wavelengths. These eruptions bombard any tightly orbiting planet with intense radiation, potentially stripping away atmospheric layers and sterilizing exposed surfaces over time. Whether Proxima b retains a meaningful atmosphere remains unknown. Whether liquid water survives on its surface remains unknown. Whether the planet is tidally locked, keeping one face permanently pointed at its star while the other freezes in permanent darkness, remains likely but unconfirmed. The world might be habitable, or it might be a scorched, airless rock, scoured clean by centuries of stellar violence. The uncertainty itself is part of the particular anguish of Proxima Centauri. There might be somewhere worth going. There might be an Earth-sized world with liquid water and a stable surface, and the raw conditions for chemistry complex enough to become biology, and it is right there, close enough to name, close enough to characterize with the instruments of the next generation, but not close enough to visit. Proxima's planetary family extends beyond Proxima b. In 2022, astronomers announced the detection of a candidate planet designated Proxima d, an exceptionally small world with a minimum mass of roughly 1/4 of Earth's, orbiting its star every 5.15 days at a distance of approximately 4 million kilometers. In 2025, the NIRPS instrument, the Near-Infrared Planet Searcher, operating at the European Southern Observatory's Very Large Telescope, independently confirmed Proxima d's existence, making it one of the least massive exoplanets ever detected through radial velocity methods. It orbits far too close to Proxima to lie within the habitable zone, and its tiny mass suggests a bare rocky body with little to no atmosphere. But its confirmation added another verified member to the Proxima system, another small world circling the nearest star. A third planet, Proxima c, was proposed in 2019 based on signals in radial velocity data, suggesting a more massive world orbiting much farther out with a period of roughly 5.2 years and a minimum mass of around 6 Earth masses. For several years, the candidate occupied an uncertain place in the literature, supported by some analyses and challenged by others. Tentative hints from Hubble Space Telescope, astrometry, and a marginal detection using the FAIR instrument added ambiguous weight to the claim, though the authors themselves acknowledged the detection was uncertain. Then, in 2025, the same NIRPS observations that confirmed Proxima d delivered a significant blow to Proxima c. The instrument was unable to confirm the radial velocity signal attributed to the third planet. Faint hints persisted, but at amplitudes too low to support the original claim. Proxima c's existence, as of now, is inconclusive at best and doubtful at worst. The confirmed planetary census matters because it defines the destination. The nearest star is not simply a point of light suspended in the void. It is a system, small and radiation-scoured, anchored by a dim red dwarf that will outlive nearly everything else in the galaxy, orbited by at least one world that might under certain conditions support liquid water, and another world so slight it represents the outer edge of what our finest instruments can resolve. The system is real, the planets are confirmed, the habitable zone candidate exists, and all of it sits at a distance so extreme that confirmation of these worlds does not bring them closer. It only makes the separation more painful. There is a particular kind of anguish in knowing precisely what you cannot reach. A prisoner who has never glimpsed the world outside suffers differently from one who can see a sunlit garden through a barred window. Proxima Centauri b is the garden. The bars are 24.9 trillion miles of vacuum, and the window is every spectrograph and telescope that confirms with increasing precision that the nearest potentially habitable world is right there, orbiting the nearest star, separated from us by a distance that transforms right there into one of the most misleading phrases in the history of human language. The astronomers who study Proxima Centauri are not being deliberately unkind. They are doing extraordinary science. The NIRPS observations that confirmed Proxima d achieved radial velocity precision measured in tens of centimeters per second, detecting the gravitational wobble of a planet lighter than Mars, tugging on a star 4.24 light-years away. The espresso spectrograph refined the mass of Proxima b to remarkable accuracy. Future observatories, including the extremely large telescope currently under construction in the Chilean Atacama Desert, may eventually characterize Proxima b's atmosphere, searching for biosignatures, chemical fingerprints that could betray the presence of biology in the light filtered through that distant world's sky. We may one day know whether Proxima b carries oxygen, whether it carries methane, whether its atmospheric chemistry whispers the existence of something alive. We will know all of this from Earth, through light, through instruments, through data traveling at the speed of electromagnetic radiation across more than 4 years of void. We will know it the way a person knows what a photograph shows. We will see it. We will analyze it. We will publish papers about it. And we will not be there. Everything described so far represents only the outermost layer of the problem. The distance, the scale, the raw physical gulf between here and the nearest star. This is the foundation on which everything else rests, and it is already staggering. But distance alone does not make the journey terrifying. Distance is a number. Numbers can be divided. Gaps can in principle be crossed. What transforms the distance from a profound challenge into something closer to a crisis is what happens the moment you try to divide it by speed. When you take this gap and ask the only question that matters for anyone who has ever dreamed of standing beneath a different sun, how long would the crossing actually take? The answer makes everything darker. In 1977, humanity launched the fastest objects it had ever aimed beyond the gravitational hold of the sun. 2 identical spacecraft, Voyager 1 and Voyager 2, departed Earth on trajectories that would carry them past Jupiter, past Saturn, and eventually out of the solar system entirely. Voyager 1 is now the most distant human-made object in existence. As of 2026, it sits approximately 173 astronomical units from the Sun, where 1 astronomical unit equals the 93 million-mile distance from Earth to the Sun. That means Voyager 1 has covered roughly 16 billion miles since the early years of the Nixon administration. It travels at approximately 17 kilometers per second relative to the Sun, around 38,000 miles per hour. That velocity is fast enough to cross the entire continental United States in about 5 minutes. Fast enough to circle Earth's equator in under 40 minutes. It is a speed so far beyond everyday human experience that it feels as though it ought to matter on interstellar scales. It does not. In late 2026, Voyager 1 is projected to reach a milestone that engineers at NASA's Jet Propulsion Laboratory have been quietly tracking for years. It will become the first human-made object to travel a full light day from Earth. A light day is the distance light traverses in 24 hours, roughly 16 billion miles or 25.9 billion kilometers. That achievement is genuine. No artifact of human civilization has ever been this far from the world that built it. But consider what the milestone actually demonstrates. Voyager 1 has been traveling for nearly 50 years, continuously, without pausing, at 38,000 miles per hour, and it has covered 1 light day. Proxima Centauri is not 1 light day away. It is approximately 1,549 light days away. Voyager 1 would need to repeat its entire 50-year journey, more than 1,500 times, end to end, without interruption, to close the distance to the nearest star. At its current velocity, the arithmetic is unambiguous. Voyager 1 would require over 73,000 years to reach Proxima Centauri. To place that in human terms, 73,000 years ago, anatomically modern humans shared this planet with Neanderthals. The last ice age had not yet reached its deepest freeze. Agriculture did not exist. Writing did not exist. The concept of a city had not occurred to anyone. Every civilization that has ever risen and collapsed on this planet, every empire, every revolution, every technological leap from the sharpened flint to the microprocessor, fits comfortably within the last 10,000 years. Voyager 1 would need 7 times that entire span simply to reach the nearest star. The whole of recorded human history is a rounding error on the journey time. Voyager 1 is not even the fastest object humanity has launched on an escape trajectory. New Horizons, which conducted its historic flyby of Pluto in 2015, was the fastest spacecraft ever launched directly from Earth, departing at roughly 16.3 kilometers per second. After a gravity assist from Jupiter, it settled into an outward trajectory that will eventually carry it beyond the solar system. But it actually travels slower than Voyager, 1 at comparable distances, because Voyager received gravitational boosts from both Jupiter and Saturn. At 100 astronomical units, New Horizons moves at approximately 13 kilometers per second, around 4 kilometers per second slower than Voyager 1. Even if New Horizons had been pointed directly at Proxima Centauri from the moment of launch, the crossing would take roughly 78,000 years, a faster departure, an equally agonizing journey. The natural question becomes, what about the absolute fastest object humanity has ever built? The Parker Solar Probe, launched in 2018 on a mission to study the Sun's outer atmosphere, holds the record for the highest velocity ever achieved by a human-made machine. During its closest approach to the Sun on the 24th of December 2024, Parker reached a speed of 191 kilometers per second. That translates to approximately 430,000 miles per hour. At that velocity, you could travel from New York to Los Angeles in under 20 seconds. You could reach the Moon in roughly 33 minutes. It is a speed that makes Voyager 1 appear nearly stationary. But context matters enormously here. Parker Solar Probe achieves this velocity only at perihelion, its closest approach to the Sun, where it dives deep into the solar gravitational field and accumulates tremendous speed from the fall. It is not traveling outward from the solar system. It is locked in a tight, elliptical orbit, screaming around the Sun and then slowing dramatically as it swings back outward. Parker's peak speed is the product of falling toward the Sun, not escaping from it. The energy required to sustain that velocity on a straight outward course toward another star would be vastly greater than anything Parker carries. But set that aside. Indulge the hypothetical. Imagine you could somehow maintain Parker Solar Probe's peak velocity of 191 kilometers per second on a direct heading toward Proxima Centauri. The distance is approximately 4.02 times 10 to the 13th kilometers. At that speed, the journey would take roughly 6,600 years, 11 times faster than Voyager, still measured in millennia. Still longer than the entire span from the construction of the Great Pyramid of Giza to the present day, by nearly half again. The fastest thing humanity has ever built, sustaining its absolute peak velocity in a direction it was never designed to travel, arrives at the nearest star in a time frame that makes the whole of recorded civilization look like a brief prologue. This is the speed problem, and it does not yield to incremental improvement. Consider the propulsion technologies that physicists and engineers have proposed for deep space travel beyond conventional chemical rockets. Nuclear thermal propulsion, in which a nuclear reactor heats propellant to extreme temperatures before expelling it to generate thrust, has been studied since the 1960s under programs like NERVA. The most capable nuclear thermal designs might achieve exhaust velocities roughly twice those of the best chemical rockets, potentially allowing spacecraft to reach speeds of perhaps 30 to 50 kilometers per second with optimal staging. That would reduce the Proxima Centauri journey from 73,000 years to perhaps 25,000 to 40,000 years. Progress, measured in geological epochs. Nuclear electric propulsion, which uses a reactor to power ion drives that accelerate charged particles to very high exhaust velocities, offers better theoretical performance. Ion drives generate tiny amounts of thrust, but can sustain it for months or years, steadily building velocity over time. The Dawn spacecraft used ion propulsion to orbit and study two separate bodies in the asteroid belt. Current ion drives achieve exhaust velocities around 30 to 50 kilometers per second, and advanced designs might push that figure to 100 or even 200 kilometers per second. If a nuclear electric spacecraft could accelerate continuously for years, it might reach cruise velocities in that range. At 200 kilometers per second, the trip to Proxima Centauri shortens to approximately 6,300 years. At 500 kilometers per second, an extremely optimistic figure, requiring propulsion systems that do not currently exist, the journey drops to roughly 2,500 years, still longer than the gap between the Roman Republic and the present day. The pattern holds without mercy. Double the speed and you halve the time, but the time is still measured in millennia. Quadruple the speed and the time is still inhuman. No extrapolation of existing chemical, nuclear thermal, or nuclear electric propulsion reduces the journey to Proxima Centauri to anything shorter than many centuries. These technologies are triumphs of engineering. They have transformed our ability to explore the solar system and everything within it. They are simply irrelevant to the demands of interstellar distance. The gap between what they can achieve and what interstellar travel requires is not a gap that better engineering can gradually close. It is a gap that requires a fundamentally different category of propulsion entirely, which brings us to the most ambitious interstellar concept ever seriously funded: breakthrough starshot. In April 2016, physicist and entrepreneur Yuri Milner stood on a stage in New York City alongside the cosmologist Stephen Hawking and announced a $100 million research initiative aimed at something that had never before attracted serious funding: sending a spacecraft to another star within a human generation. The concept was audacious in the most literal sense: build a ground-based laser array capable of producing 100 gigawatts of coherent light. Use that array to accelerate gram-scale spacecraft, each fitted with an ultra-thin reflective sail roughly 4 meters across, to 20% of the speed of light. At approximately 60,000 kilometers per second, a probe would reach Proxima Centauri in roughly 20 years. Add 4.24 years for the return data transmission, and the total mission time from launch to first results sits at about 24 years. Within a single career, within a generation that could watch the whole thing unfold. The announcement generated genuine excitement across the scientific community and the public imagination. Here was a credible, funded, scientifically grounded proposal to reach the nearest star in a time frame that living human beings could actually experience. The advisory board included Hawking and Facebook co-founder Mark Zuckerberg. The committee was chaired by Harvard astrophysicist Avi Loeb. Serious researchers from serious institutions were involved and working. The engineering challenges, however, were equally serious. Building a laser array that combines thousands of individual laser sources into a single coherent beam carrying 100 gigawatts, a power output comparable to the total electricity consumption of a mid-sized country, requires advances in photonics, beam combining, and atmospheric compensation that do not currently exist. The sails must be fabricated from materials capable of reflecting the laser energy efficiently enough to accelerate without being destroyed by the beam's intensity. The probes must carry cameras, communication systems, navigation instruments, and power sources within a total mass budget of a few grams. Each probe must survive acceleration forces of approximately 10,000 times Earth's gravity during a boost phase lasting around 10 minutes. Once at cruise velocity, the probes must endure 2 decades of transit through the interstellar medium, where even individual hydrogen atoms and microscopic dust grains become high-velocity projectiles, striking the sail and hull at 20% of the speed of light. At that velocity, a dust grain massing 1 microgram carries kinetic energy equivalent to several sticks of dynamite detonating against the structure. Over 20 years and 4.24 light-years of space that is sparse but not perfectly empty, cumulative damage from such impacts becomes a genuine threat to mission survival. Then there is the communication problem. A gram-scale probe at Proxima Centauri must transmit its data back to Earth across 4.24 light-years using a laser or radio system constrained by the mass and power budget of a device smaller than a smartphone. Researchers associated with the project have estimated that data rates on the order of roughly 1 kilobit per second might be achievable using onboard laser communications and a large receiving array on Earth, yielding a data return of perhaps a few gigabytes per year. That is broadly comparable to what New Horizons transmitted after its Pluto encounter, enough for images and basic scientific measurements. But even that modest rate requires pointing a communications laser from a chip-scale spacecraft across interstellar distances with extraordinary precision, hitting a receiving station that, from the probe's perspective, is an invisible speck lost somewhere in the glare of the sun. For roughly 9 years, Breakthrough Starshot funded studies, convened scientific meetings, and made incremental progress on specific technical problems. Researchers demonstrated coherent beam combining with tens of individual lasers in laboratory conditions. Scientists at Caltech performed the first direct radiation pressure measurements on miniature light sail membranes, a foundational experimental step published in early 2025. Prototype Sprite spacecraft, tiny centimeter-scale circuit boards representing early ancestors of the envisioned probes were launched to orbit and successfully operated. Advances in light sail materials, optical fabrication techniques, and beta-voltaic nuclear batteries for onboard power were investigated and refined. Then, in September 2025, Scientific American reported that Breakthrough Starshot had entered a state of indefinite suspension. Philip Lubin, one of the project's lead researchers at the University of California, Santa Barbara, estimated that the program had spent roughly $4.5 million of its proposed $100 million budget across approximately 30 research contracts. Activity had peaked during the first 4 or 5 years and then quietly faded. Meetings stopped. Communications went silent. No formal termination was announced, but no continuation was evident either. A promised comprehensive report on the project's status had not materialized by the time the article went to press. As of early 2026, the trajectory of Breakthrough Starshot remains unclear. Researchers involved with the project describe it as a success in the sense of advancing the science of interstellar propulsion and establishing interstellar travel as a legitimate engineering goal rather than a purely speculative fantasy. But the hardware required for an actual mission, the 100-gigawatt laser array, the flawless light sails, the gram-scale probes capable of surviving relativistic transit and transmitting data across light years, remains decades away, under even the most optimistic assessments. The total mission cost, initially estimated by Milner at $5 to $10 billion, would almost certainly be far higher. What Breakthrough Starshot ultimately reveals about the speed problem is this. Even in its most optimistic form, the most ambitious interstellar mission ever funded, backed by a billionaire, advised by some of the world's leading physicists, targeting only a gram-scale robotic flyby with no deceleration and no return, struggled to clear the first engineering thresholds with $100 million over nearly a decade. The concept remains physically permissible. The laws of physics do not forbid it. But the distance between theoretical permissibility and functional hardware is vast, and the timeline for closing that distance stretches well beyond any near horizon. 20% of the speed of light is not something humanity can produce today. It is something humanity might produce in several decades if the funding, the political will, and the necessary engineering breakthroughs all converge simultaneously. And even then, the result is a flyby, a fleet of chip-sized objects screaming past Proxima Centauri at 60,000 kilometers per second, gathering a few hours of close-range data before vanishing into the void forever. No orbit, no landing, no return. A brief, extraordinary glimpse, purchased with decades of development and billions of dollars. Now, set aside probes entirely. Forget chips and light sails and laser arrays. Ask the question that science fiction has trained every generation to ask, and that physics refuses to answer gently. What about sending people? A crewed mission to Proxima Centauri is not a harder version of the same problem as a robotic flyby. It is a different problem. A probe can be built to weigh a few grams. A crewed vessel must be enormous. It must carry human beings, which means it must carry atmosphere, water, food, medical supplies, radiation shielding, exercise facilities, waste processing systems, redundant life support, and enough spare components to maintain all of these systems for the full duration of the journey. It must carry propulsion systems massive enough to accelerate this entire payload to interstellar cruise velocity. And then, it must decelerate upon arrival, because human beings cannot survive a flyby at 20% of the speed of light. They need to stop. And stopping requires carrying roughly as much fuel as accelerating, which increases the total mass, which demands more fuel to move the additional mass, which increases the total mass further, cascading in a cycle that rocket engineers call the tyranny of the rocket equation. The deceleration problem alone transforms the mission architecture beyond recognition. A robotic flyby probe accelerates to cruise speed and never slows down. It screams past the target, captures what data it can during a few hours of close approach, and continues into the void. A crewed vessel cannot do this. The crew must arrive at Proxima Centauri with enough residual control over their velocity to enter orbit, or at minimum, a manageable trajectory toward a planetary destination. That means the ship must perform a braking maneuver that reduces its speed from interstellar cruise velocity back towards something survivable. The fuel required for that deceleration burn is roughly equal to the fuel required for the initial acceleration. But carrying that deceleration fuel means the ship is heavier at departure, which means the initial acceleration burn must push more mass, which requires still more fuel. The rocket equation converts this into an exponential spiral that rapidly leaves any physical intuition behind. For chemical rockets, the mass ratios become physically absurd within a few kilometers per second of velocity change. For nuclear or fusion drives with higher exhaust velocities, the ratios improve but remain punishing at interstellar scales. A ship that must accelerate to 5% of light speed and then decelerate back to zero requires a mass ratio that, depending on the propulsion system, could mean the fuel outweighs the payload by factors of dozens or hundreds. The ship becomes mostly fuel. The habitable section, the life support, the crew, the scientific instruments, everything that gives the mission its human meaning shrinks to a fraction of the total vessel mass. A small kernel of purpose buried inside a mountain of propellant. To understand what that spiral actually produces, walk through the mass budget of a single concrete mission profile. Imagine a crew of 50 people traveling to Proxima Centauri at 5% of the speed of light, roughly 15,000 kilometers per second, using an advanced fusion drive with an exhaust velocity of 5,000 kilometers per second. That exhaust velocity lies far beyond anything that currently exists, but it sits within the theoretical boundaries of deuterium, helium, 3 fusion reactions. The journey takes approximately 84 years. The crew needs a habitat. Start there. 50 people require living quarters, communal areas, exercise facilities, medical bays, laboratories, food production modules, water recycling systems, atmospheric processing equipment, waste management infrastructure, power generation, and enough physical volume to preserve psychological health across decades of confinement. Based on estimates drawn from long-duration spaceflight research, a minimum of roughly 1,000 cubic meters of pressurized volume per person is necessary for a mission of this length. That gives 50,000 cubic meters of pressurized habitat in total. The structural mass for this habitat, including pressure vessels, internal partitions, flooring, equipment mounting frameworks, and all the mechanical and electrical systems integrated into the structure, comes to roughly 5,000 metric tons. That is the bare skeleton of the living space before a single piece of equipment is placed inside it. Now add life support, atmospheric processing systems, water recycling plants, hydroponic food production modules, waste treatment infrastructure, thermal regulation equipment, and full backup units for every one of these systems. The International Space Station's life support hardware masses roughly 20 metric tons and sustains 6 people during 6-month increments, with regular resupply from Earth. A system that must support 50 people for 84 years with no resupply whatsoever must be radically more capable, more redundant, and far more massive. Estimates place this component at roughly 3,000 to 5,000 metric tons, depending on how much food production is handled by onboard agriculture versus preloaded provisions. Add radiation shielding. The habitat must be encased in several meters of hydrogen-rich material to reduce galactic cosmic ray exposure to levels the crew can survive across an 84-year transit. Water is the most practical shielding material because it serves double duty as a consumable resource. Surrounding a 50,000 cubic meter habitat with a water shield 3 meters thick on all exterior surfaces adds roughly 150,000 metric tons of water to the vessel's mass. The shielding alone outweighs the habitat structure by a factor of 30. Without it, the crew accumulates lethal radiation exposure within a decade or two. Add spare components, onboard manufacturing equipment, raw material stocks for fabrication, medical supplies sufficient for 84 years, seed reserves for food production, precision tools, scientific instruments, communication arrays, and the countless other consumables and contingency stores required for a self-sustaining community that can never receive a delivery from anywhere. A conservative estimate places this category at 5,000 to 10,000 metric tons. The payload, meaning the total mass of everything aboard the vessel that is not propellant, now sits at roughly 165,000 to 170,000 metric tons. Call it 170,000 metric tons for clarity. This is the mass the propulsion system must accelerate to 5% of the speed of light and then decelerate back to zero at the destination. Now apply the rocket equation. The Tsiolkovsky rocket equation states that the ratio of a vehicle's initial mass to its final mass equals the mathematical constant e raised to the power of the total velocity change divided by the exhaust velocity. For a mission that must accelerate to 15,000 kilometers per second and then decelerate back to zero, the total velocity change is 30,000 kilometers per second. With an exhaust velocity of 5,000 kilometers per second, the exponent is 6. E to the sixth power equals approximately 403. That means for every single metric ton of payload that arrives at Proxima Centauri, the ship must begin its journey carrying 403 metric tons at departure. Multiply the 170,000 metric ton payload by 403. The total departure mass is approximately 68.5 million metric tons. 68.5 million metric tons. That is roughly the mass of a modest metallic asteroid. More than 99.7% of that mass is fusion fuel. The habitat, the crew, the radiation shielding, the life support systems, everything that makes the mission recognizably human, accounts for less than 1/4% of the vessel's total mass at launch. The ship is not a spacecraft that carries a fuel tank. It is a fuel tank that carries a spacecraft somewhere deep within it. A small, warm pocket of human life embedded inside an almost incomprehensibly vast reservoir of propellant. And this estimate rests on a fusion drive with an exhaust velocity of 5,000 kilometers per second, a propulsion technology that does not exist. If the exhaust velocity is lower, say 1,000 kilometers per second, which sits closer to what near-term advanced propulsion concepts might actually achieve, the mass ratio explodes to E raised to the 30th power. That number exceeds any physically meaningful quantity of matter available in the solar system. The mission does not become more difficult. It becomes mathematically impossible without propulsion performance that currently belongs entirely to the domain of theoretical physics. This is what the rocket equation does to crewed interstellar travel. It converts an 84-year journey for 50 people into a 68 million metric ton engineering undertaking. And that is the optimistic version, constructed around propulsion technology that has not been invented, using fuel that has not been produced in anything approaching the required quantities. The vessel would need to be assembled in space over the course of decades. The fuel itself, helium-3 inches the quantities required, would likely need to be extracted by mining the lunar surface or the upper atmospheres of the outer gas giants, an industrial undertaking that dwarfs every infrastructure project in human history combined. The economic cost, measured in present-day terms, would almost certainly exceed the gross domestic product of the entire planet across multiple years of sustained effort. And at the end of all of that, the result is a ship that crawls toward the nearest star at 5% of the speed of light, requiring 84 years to arrive, crewed by people who will overwhelmingly die in transit. The habitable section of such a vessel presents engineering challenges that have no parallel in the history of human construction. On the International Space Station, roughly 400 cubic meters of pressurized volume supports a rotating crew of 6 during missions lasting 6 months. The station is resupplied every few weeks. Food, water, spare components, experimental equipment, fresh clothing, and occasional small luxuries arrive regularly from Earth's surface. Waste is removed. Air is partially recycled but supplemented from external sources. Water is recycled, but not with perfect efficiency. The station maintains its relationship with Earth the way a deep-sea diver maintains a connection to the surface. The tether is long, but it is never cut. A crewed interstellar vessel cannot be resupplied. Everything the crew will consume across the next 40, 60, or 100 years must either be aboard at departure or grown during the journey. Closed-loop life support. in which air, water, and nutrients are recycled with near-perfect efficiency over indefinite timescales, has never been achieved at the scale or duration the mission demands. The most ambitious closed ecosystem experiment in human history, Biosphere 2 Inches Arizona, attempted to sustain 8 people inside a sealed 3-acre habitat for 2 years beginning in 1991. It failed. Oxygen levels dropped to dangerous concentrations, carbon dioxide spiked, crops underperformed, insect pollinators died off. The experiment required 2 emergency injections of oxygen from outside the sealed environment. 2 years, 8 people, 3 acres of carefully engineered biome, and the system could not sustain itself without external intervention. An interstellar vessel must accomplish what Biosphere 2 could not, at a smaller scale, over a vastly longer duration, in an environment where external intervention is physically impossible by definition. The habitat must also provide sufficient space for psychological integrity across decades. Research drawn from submarine operations, Antarctic winter overstations, and long-duration spaceflight consistently demonstrates that prolonged confinement in constrained environments degrades cognitive function, intensifies interpersonal friction, and erodes motivation over time. The minimum viable living space for a multi-decade crewed mission is not a capsule. It is a small town, exercise facilities, medical bays, laboratories, recreation areas, private quarters, food production modules, water processing infrastructure, waste recycling systems, power generation and storage, communication equipment, navigation and propulsion control rooms, and enough structural redundancy that the failure of any single module does not kill everyone aboard. Estimates for the minimum pressurized volume appropriate for a crew of 50 on a multi-decade mission range from tens of thousands to hundreds of thousands of cubic meters. The structural mass alone, before adding life support equipment, propellant, shielding, and consumables, reaches thousands of metric tons. The total departure mass for even a modest crewed interstellar mission climbs into the tens of millions of metric tons once the rocket equation applies its merciless multiplication to the fuel requirements. Even the most optimistic designs for crewed interstellar vehicles in the engineering literature envision vessels of extraordinary scale. Project Daedalus, a detailed study conducted by the British Interplanetary Society through the 1970s, designed an uncrewed fusion-powered probe intended to reach Barnard's star in roughly 50 years at 12% of the speed of light. The vehicle itself would have massed over 50,000 metric tons, the overwhelming majority of which was fuel in the form of deuterium and helium, 3 pellets. And Daedalus was not designed to carry people. It was not designed to slow down. It was a flyby probe, simply a far larger one than Breakthrough Starshot envisions. Scaling Daedalus to include a habitable section, deceleration capability, and life support for even a minimal crew would multiply the mass by orders of magnitude. Project Longshot, a study conducted at the United States Naval Academy in the late 1980s, proposed a smaller fusion-powered probe to the Alpha Centauri system, requiring roughly 100 years to arrive. Again uncrewed. Again no deceleration to orbit. The engineering challenges for even these stripped-down robotic concepts remain well beyond current capabilities. Controlled fusion propulsion, the engine at the heart of both designs, has not been achieved in any practical operational form, despite decades of sustained research and billions of dollars of investment. The International Thermonuclear Experimental Reactor, currently under construction in southern France, aims to demonstrate sustained fusion energy release, but is not expected to produce net energy until the 2030s at the earliest. And the leap from a stationary ground-based fusion reactor to a flight-rated fusion engine compact and reliable enough for deep space propulsion is enormous. If controlled fusion propulsion were somehow mastered and miniaturized for spaceflight, the most optimistic crewed mission profiles suggest cruise velocities of perhaps 5 to 10% of the speed of light. At 10%, the journey to Proxima Centauri takes roughly 42 years. At 5%, 84 years. These numbers sit, for the first time, within the nominal span of a human lifetime, at least in principle. but they require technologies that do not exist, fuel sources that have not been developed in usable quantities, and engineering solutions to problems that have not been solved. They require building the largest, most complex, most reliable machine in the history of the species, and operating it without critical failure for decades, in an environment where a single catastrophic malfunction means the death of everyone aboard, with no possibility of rescue, repair, or resupply from any direction. And even these optimistic timelines assume the vessel reaches its target velocity almost immediately after departure. In reality, acceleration would consume weeks, months, or years depending on the propulsion system's thrust output. Deceleration at arrival would demand equal time and fuel expenditure. A more realistic mission profile for a crewed, fusion-powered vessel might extend the total journey to 60, 80, or over 100 years, even at velocities approaching 10% of light speed. 100 years in a sealed vessel crossing the silence between stars. The people who launch would not be the people who arrive. Their children might not be the people who arrive. This is no longer a mission in any recognizable sense of the word. It is a commitment that spans generations. It asks human beings to board a ship, understanding they will die in transit, understanding their children will be born, will grow to adulthood, and will die inside those same corridors, understanding that only some future generation, people who never made this choice and never knew the Earth their ancestors departed from, might one day walk beneath a different sky. The vessel does not merely cross a distance, it becomes a world unto itself, a sealed ecosystem, a society, a civilization compressed into a hull and aimed at a point of light 4.24 light-years away, hurtling through emptiness for longer than most nations on Earth have existed. This is what the speed problem ultimately means when applied to human beings rather than machines. It is not simply that humanity cannot yet travel fast enough. It is that the velocities required to make the journey bearable by any recognizable human standard demand propulsion systems that have not been invented, energy sources that have not been harnessed, and engineering reliability that has never been demonstrated across the necessary timescales. Every plausible technology produces a journey measured in decades at the extreme optimistic minimum and millennia at the realistic maximum. And the shorter the journey time, the more extreme the engineering requirements, the more massive the vessel, the more catastrophic the consequences of any failure along the way. The speed problem is not a challenge that will yield to a better engine alone. It is a problem that exposes the fundamental mismatch between the distances the universe imposes, between its stars and the timescales that human biology, human psychology, and human engineering can sustain. Voyager 1 will travel for 73,000 years and still not arrive. Parker's solar probe at its peak velocity would require 66 centuries. The best nuclear concepts reduce the journey to thousands of years. Fusion propulsion, if it ever becomes real, might compress it to decades, but only for machines, and only at the cost of constructing something without precedent in human history. For a crewed vessel, the cost is a 68 million metric ton structure that is 99% fuel, carrying a pocket of human life smaller than a city block, crawling through darkness for the better part of a century. And yet, the speed problem, as severe as it is, describes only part of what the journey demands. Because even if you solve it, even if you build the engine and fuel the ship and accelerate to 10% of the speed of light and point the vessel toward Proxima Centauri, you have addressed only how long the crossing takes. You have not addressed what the crossing does to the people inside. You have not addressed what happens when something breaks and no assistance is possible. You have not addressed what it means to transmit a message toward Earth and wait nearly a decade for any reply. You have not addressed what the void itself, the lightless, soundless, featureless space between stars, does to human minds sealed inside a metal shell for a lifetime. The distance is the foundation, the speed is the sentence, but the true weight of the journey to Proxima Centauri lives in what comes next. On the International Space Station, Astronauts live and work approximately 250 miles above Earth's surface. If something goes catastrophically wrong, if a micrometeorite punctures the hull, if a fire erupts in a module, if a crew member suffers a medical emergency requiring immediate intervention, the response time is measured in hours. A Soyuz or Crew Dragon capsule is always docked and ready. From the moment an evacuation decision is made, the crew can be back on Earth's surface in under 4 hours. Depending on orbital geometry, an emergency landing can occur in as little as 90 minutes. The ground is right there, visible through every window, close enough that astronauts report being able to distinguish individual cities glowing in the darkness below. This proximity is not incidental to the International Space Station's success. It is foundational to everything the station does and everything it represents. Every system aboard, every redundancy protocol, every emergency procedure, every element of the psychological support structure built around long-duration missions depends on the simple and irreducible fact that Earth is minutes away. Help is real. Return is possible. Home is visible. Now move outward. On a mission to the Moon, the communication delay runs to roughly 1.3 seconds in each direction. You speak, and 2.6 seconds later you hear the reply. Noticeable, but workable. Apollo astronauts held real-time conversations with mission controllers in Houston. The delay introduced only a slight awkwardness into the rhythm of exchange. Emergency return from the lunar surface takes approximately 3 days. Not immediate, not effortless, but survivable, plannable, and already demonstrated by 12 human beings who walked on another world and came home. Move farther still. Mars sits between 4 and 24 light-minutes away depending on where both planets stand in their respective orbits. A round-trip exchange takes between 8 and 48 minutes. Real-time conversation becomes impossible. Every communication reduces to a series of monologues separated by long silences. Mission planners for future crewed Mars missions have grappled seriously with the psychological weight of this delay, recognizing that it fundamentally transforms the relationship between crew and ground support. An astronaut on Mars facing an unexpected system failure must act on local knowledge alone, waiting many minutes for any guidance to arrive from Earth. Help can eventually come. Resupply missions can be launched on the next available transfer window. Evacuation vehicles can be prepositioned, but nothing happens quickly, and Mars is the first destination where the tether connecting crew to civilization begins stretching towards something that feels precarious. At Proxima Centauri, the tether does not stretch, it breaks. A radio signal or laser pulse, traveling at the speed of light from Proxima Centauri to Earth, requires 4 years, 3 months, and approximately 1 week to complete the journey. 4.24 years, one direction. A round-trip exchange, sending a question and waiting for an answer, requires 8.48 years. Consider what that means in terms that actually register. If a crew arriving at Proxima Centauri transmits a message saying they have reached the destination safely, the people who receive that message on Earth will be living in a world that has changed profoundly since the words were spoken. Governments will have changed. Technologies will have advanced. Children born on the day the transmission was sent will be entering their 3rd year of primary school by the time the signal arrives. The crew's families will have aged by more than 4 years. Some will have died. And the reply, when it finally returns another 4.24 years after that, will describe an Earth nearly a decade removed from the moment the crew first reached out. Every conversation becomes a time capsule opened years too late. This is not a communication inconvenience, it is a severing of the most fundamental kind. On the International Space Station, an astronaut can place a call and hear a child's voice in real time. On Mars, a message can be sent and answered within the same day, or at worst the same week. At Proxima Centauri, a parent aboard the ship could record a birthday message for a child on Earth and receive that child's response when the child is 8 years older than when the message was sent. The natural rhythm of human connection, the call and reply of conversation, the immediate emotional feedback that allows people to feel genuinely linked across distance, dissolves entirely across 4.24 light years. What survives is correspondence. letters sent into a void and answered by people who share your memories but no longer share your present moment, who have lived nearly a decade of life that you will never witness, never know, never be part of. And this delay is not merely emotional, it is operationally catastrophic. If the crew encounters a system failure they cannot diagnose, they can transmit all available data to Earth and wait. The finest engineers on the planet will analyze the problem, develop solutions, and transmit instructions back. The crew will receive those instructions 8.48 years after the problem first appeared. If the problem involved life support, propulsion, power generation, or hull integrity, waiting 8.48 years is not a delay. It is a death sentence delivered with unusual patience. The crew must resolve every crisis using only the people, the tools, the spare components, and the accumulated knowledge that departed with them. Mission control becomes something closer to a historical archive, a source of commentary on events that resolved themselves, one way or another, years before the commentary arrived. The ground team cannot guide in real time, cannot intervene, cannot send anything physical across the void. They can only observe, years after the fact, and hope. This operational isolation places the mission in a category that has no genuine precedent in the history of human exploration. Every expedition before it, from Magellan's circumnavigation to the Apollo lunar landings, maintained some functional connection to the civilization that launched it. Magellan's ships could encounter other vessels, could resupply at ports, could receive information from passing traders. Apollo astronauts were in continuous radio contact with Houston throughout every phase of every mission. Even the most remote Antarctic research stations receive supply flights and maintain satellite communication links to the outside world. No human undertaking has ever operated in true isolation, genuinely beyond the reach of any assistance, for years at a stretch. A crew bound for Proxima Centauri would be the first human beings in history for whom the word alone described not a feeling, but a physical fact of the universe. Not alone in the sense of being far from people who care about them. Alone in the sense that no other human being anywhere in existence can reach them, assist them, resupply them, rescue them, or even speak to them in anything resembling real time. The nearest other humans would be separated by a gulf that no ship, no signal, no act of will can bridge within any meaningful time frame. The impossibility of rescue deserves its own careful reckoning, because it represents a psychological boundary that human beings have never before been asked to cross. On every dangerous expedition in recorded history, some theoretical possibility of rescue existed. Ernest Shackleton's crew, stranded on the Antarctic ice after the Endurance was crushed in 1915, survived in part because Shackleton could sail an open lifeboat to South Georgia Island and summon help from there. Even in the worst maritime disasters, passing vessels might spot survivors. Even on the most remote mountain face, a helicopter might eventually arrive. This possibility, however remote, changes how humans experience danger. It allows hope to function. It provides a cognitive anchor, a background understanding that if everything fails, someone might still come. At Proxima Centauri, no one is coming. If the crew transmitted a distress signal the moment they arrived, the fastest conceivable rescue vessel using technologies that do not yet exist would require decades to reach them. By the time any help arrived, the original crew would in all likelihood have died of age, even if the initial emergency had not already killed them. Rescue is not merely improbable, it is excluded by physics. The speed of light imposes a minimum response time measured in years. The speed of any physical vessel imposes a response time measured in lifetimes. The concept of rescue, as human beings have always understood it, has no meaning at interstellar distances. This reality reshapes every engineering decision the mission demands. On Earth-orbiting missions, systems are designed with the knowledge that failure can be survived through evacuation. On an interstellar mission, every system must be designed with the knowledge that failure means death, unless the crew can repair it themselves, using only what they brought. Redundancy cannot be selective. Spare components cannot cover only the most likely failure modes. The crew cannot be trained as specialists, supported by expert ground teams. They must function as a self-sufficient civilization capable of manufacturing, diagnosing and improvising solutions to problems that no one anticipated, using only the materials present at departure. This engineering philosophy differs fundamentally from anything humanity has practiced in spaceflight. It resembles less the challenge of operating a spacecraft and more the challenge of sustaining a colony in a place where no resupply is ever coming. Beyond the isolation, the physical environment of interstellar space presents hazards that begin the moment the vessel crosses the outer boundary of the heliosphere. Our Sun generates a continuous outflow of charged particles known as the solar wind, which inflates an enormous bubble around the entire solar system called the heliosphere. Inside this bubble, the solar wind's embedded magnetic field deflects a meaningful fraction of the galactic cosmic rays that permeate interstellar space. The heliosphere is not a perfect shield. Cosmic ray particles still penetrate it in significant numbers, and astronauts aboard the International Space Station receive measurably elevated radiation doses compared to people on Earth's surface. But the heliosphere provides genuine protection, particularly against the most energetic and biologically damaging particles. Beyond the heliosphere, that protection vanishes entirely. Voyager 1 crossed the heliopause, the outermost boundary of the heliosphere, in August 2012 at approximately 122 astronomical units from the Sun. Its instruments registered an immediate and sharp increase in the intensity of cosmic ray bombardment. The interstellar medium is saturated with galactic cosmic rays, particles accelerated to enormous energies by supernova remnants, neutron stars, and other violent astrophysical processes distributed throughout the Milky Way. These particles include protons, helium nuclei, and heavier atomic nuclei, traveling at significant fractions of the speed of light. When they strike living tissue, they shatter DNA strands, cause mutations, overwhelm cellular repair mechanisms, and over sustained exposure dramatically elevate cancer risk, neurological deterioration, and a range of other radiation-related pathologies. The biological damage produced by galactic cosmic rays differs qualitatively from radiation hazards familiar to humans in other contexts. On Earth's surface, the atmosphere and magnetosphere block nearly all cosmic ray particles before they reach ground level. In low Earth orbit, the magnetosphere still provides partial deflection. Beyond the heliosphere, nothing stands between the crew and the full, unattenuated flux of galactic radiation. The most dangerous component consists of heavy ions, atomic nuclei of elements such as iron and silicon stripped of their electrons and accelerated to near-light velocities. When one of these particles passes through living tissue, it does not deposit energy along a narrow track the way a medical X-ray does. It creates a column of severe molecular destruction through every cell in its path, shattering chemical bonds, generating cascades of reactive molecular fragments, and leaving a trail of cellular damage that the body's repair mechanisms are poorly equipped to address. A single heavy ion passing through a cell nucleus can produce complex DNA damage at multiple locations simultaneously. The kind of damage most likely to result in permanent mutation or cell death, rather than successful repair. Over the course of a multi-decade journey, every cell in every crew member's body would be traversed by these particles multiple times. The cumulative effect is not a single dramatic event, but a slow, persistent degradation of biological integrity. Cancer risk rises substantially. Cataracts form as radiation damages the transparent cells of the eye's lens. Cardiovascular tissue sustains cumulative injury that may accelerate heart disease decades before it otherwise would. And perhaps most troublingly, for a mission that demands sustained cognitive performance, the central nervous system suffers progressive damage that manifests as impaired memory formation, reduced processing speed, diminished reaction time, and increased susceptibility to neurological disorders. Animal studies exposing rodents to simulated galactic cosmic ray environments have demonstrated measurable cognitive impairment after exposure levels equivalent to what a crew would accumulate over a few years of unshielded interstellar transit. The crew would not merely face an elevated lifetime cancer probability, they would face a progressive erosion of the very mental acuity they need to operate and maintain the most complex machine ever built. In an environment where cognitive failure can cascade directly into physical catastrophe. Protecting against galactic cosmic rays is far more difficult than shielding against solar radiation. Solar particles are relatively low in energy and can be stopped by modest material thickness. Galactic cosmic rays are far more energetic. They penetrate meters of solid matter, and worse, when high-energy particles strike dense shielding materials such as metal, they trigger secondary radiation events, showers of neutrons and other particles that can be more biologically damaging than the original cosmic ray that initiated them. This phenomenon, called secondary particle production, means that simply adding more metallic shielding can actually increase the radiation dose received inside the ship rather than reducing it. The most effective shielding strategy for galactic cosmic rays involves hydrogen-rich materials such as water or polyethylene, which absorb incoming particles without generating as many dangerous secondaries. But effective shielding requires substantial thickness, on the order of several meters of water-equivalent material surrounding the entire habitable volume. The mass penalty is severe, adding many thousands of metric tons to a vessel already straining under the weight of the rocket equation's demands. Some mission concepts propose generating artificial magnetic fields around the spacecraft to deflect charged particles, mimicking the function of Earth's magnetosphere on a small scale. These concepts are theoretically attractive, but present engineering difficulties of the first order. Generating a magnetic field strong enough to deflect galactic cosmic rays over a volume large enough to protect a crude habitat requires superconducting magnets of extraordinary scale and power, maintained at cryogenic temperatures without interruption for decades. Nothing approaching the required scale has ever been demonstrated. The interstellar medium presents a second distinct physical hazard that compounds the radiation problem. The space between stars is not perfectly empty. It contains a sparse but measurable distribution of hydrogen atoms, roughly 1 atom per cubic centimeter, in the local interstellar environment near our solar system, along with microscopic dust grains typically measuring fractions of a micrometer and composed of silicate minerals, carbon compounds, and frozen volatile materials. At low velocities, these particles are entirely harmless. At the cruise speeds required for interstellar travel, they become something else entirely. Kinetic energy scales with the square of velocity. A dust grain massing 1 microgram, far smaller than a grain of beach sand, striking a spacecraft traveling at 10% of the speed of light, delivers kinetic energy, roughly equivalent to a small automobile colliding with a wall at highway speed. The ship does not encounter one such particle. It encounters a continuous stream of them across years or decades of transit. Each impact erodes shielding layers, degrades exposed surfaces, and risks penetrating systems critical to crew survival. The cumulative effect of billions of such collisions over a 20-year journey at 10% of light speed could be structurally catastrophic. At 20% of light speed, the energy per impact quadruples. A gram-scale breakthrough Starshot probe might tolerate some degree of surface erosion during its brief transit. A crewed vessel, which must arrive structurally intact and fully functional, faces a challenge of an entirely different magnitude. The forward-facing surfaces of the hull must withstand a sustained, relativistic bombardment that no terrestrial material has ever been tested against at these velocities, validated through engineering trials that have never been attempted. And then there is the question of mechanical endurance across timescales that no human machine has ever been asked to survive. The Voyager spacecraft illuminate this problem with uncomfortable clarity. As of 2026, both Voyagers are approaching 50 years of continuous operation in deep space. They have been extraordinary engineering achievements, but they are failing. Voyager 1 now operates with only 2 scientific instruments still functional. Heaters have been progressively shut down to conserve the dwindling power output of its radioisotope thermoelectric generators. Backup systems have been exhausted one by one. Thruster fuel lines are showing signs of clogging. In October 2024, a fault protection event shut down Voyager 1's primary X-band transmitter, temporarily reverting communications to its backup S-band system, which had last been used in 1981. engineers managed to restore the X-band link after weeks of careful troubleshooting across a signal delay approaching 23 hours each way. Between May 2025 and February 2026, the only antenna on Earth capable of transmitting commands to Voyager, Deep Space Station 43 inches, Canberra, Australia, was taken offline for maintenance, leaving both spacecraft unable to receive instructions for months. 50 years, 2 instruments remaining, clogging thrusters, a transmitter that nearly failed permanently, single-string systems with no remaining backups. And these are spacecraft that carry no crew, require no life support, operate no complex mechanical systems beyond thrusters and antenna positioning, and mass less than a metric ton each. A crewed interstellar vessel would be orders of magnitude more complex in every dimension. It would contain atmospheric processing systems, water recycling plants, food production infrastructure, thermal management networks, power generation and distribution systems, waste processing equipment, medical facilities, communication arrays, navigation computers, propulsion systems, structural health monitoring sensors, airlock mechanisms, and the dense web of interdependencies connecting all of these systems to one another. Every one of them would need to operate without any critical failure for the entire duration of the journey. Decades at minimum, a century or more in many realistic scenarios. No human-built system has ever demonstrated reliability of that order across those timescales. Every piece of industrial machinery on Earth is maintained, repaired, overhauled, and eventually replaced. Components wear, seals degrade, bearings fail, electronics accumulate radiation damage that corrupts their function over years. Software encounters unforeseen combinations of conditions that produce unexpected behavior. Structural materials develop fatigue cracks under repeated stress cycling. The longer any complex machine operates without maintenance from outside, the more certain failure becomes. And that probability does not merely accumulate linearly, it compounds across thousands of interdependent subsystems, each failure changing the conditions under which every other system must operate, each repair consuming resources that cannot be replaced. The crew could carry spare components. They could carry fabrication equipment capable of manufacturing certain replacement parts. They could train as mechanics, electricians, physicians, chemists, and structural engineers. But they cannot carry spares for every possible failure mode. They cannot anticipate every way a system might degrade across 80 years of exposure to an environment no machine has ever operated in for that duration. Some components will fail in modes no one predicted. Some materials will behave in ways that only become apparent after decades of combined radiation exposure, thermal cycling, and mechanical stress. And when those failures occur, the crew must diagnose and solve them, using only what they carried at departure. The ship is not a vehicle. It is a closed world, and closed worlds that cannot be resupplied are subject to a principle that admits no exceptions. Entropy wins eventually. The only question is whether the people inside can slow its advance long enough to reach what waits at the other end of the darkness. This brings the journey to its most intimate and perhaps most devastating dimension, the human mind. Space psychology is a mature discipline built on decades of accumulated research into how human beings respond to confinement, isolation, monotony, danger, and prolonged separation from familiar environments. The findings are consistent across every context in which they have been gathered, and they are sobering without exception. Even short-duration space missions produce measurable psychological effects. Astronauts completing 6-month increments aboard the International Space Station regularly report disrupted sleep, interpersonal tension with crewmates, cognitive fatigue, and periods of low mood that require active management. These effects emerge during missions where the crew knows exactly when they are going home, where they can see the Earth turning slowly below them through every window, and where a psychologist is available by radio within seconds. Longer simulation studies deepen the picture considerably. The Mars 500 experiment, conducted in Moscow between 2010 and 2011, confined 6 volunteers inside a sealed habitat for 520 days to simulate the psychological conditions of a round-trip Mars mission. Participants experienced depression, progressive social withdrawal, severely disrupted sleep-wake cycles, and escalating interpersonal friction as the months accumulated. As the experiment moved into its later stages, one participant became so sedentary and disengaged that researchers classified his behavioral pattern as consistent with chronic depression. These effects emerged in a controlled environment where every participant knew they were on Earth, knew they could exit the habitat if the situation became genuinely dangerous, and knew the experiment had a fixed end date. An interstellar crew would have none of those psychological safety structures in place. There is no exit. There is no fixed end date visible from within the journey. There is no ground control psychologist available for a real-time conversation. The daily sensory environment of an interstellar vessel would be impoverished in ways that compound every other psychological burden the journey imposes. The lighting would be artificial throughout, calibrated to approximate a diurnal cycle, but never varying the way natural light does across seasons and latitudes. Never the long golden quality of late afternoon falling through a window. Never the soft grey diffusion of an overcast morning. Never the slow deepening of a winter dusk that tells the body, without words, that the world is turning and time is moving. The air would be mechanically recycled and filtered, always carrying the faint background scent of polymer outgassing and filtration systems working continuously in the walls. The sounds would be the perpetual hum of air handlers, the low structural vibration of systems under load, the occasional click and hiss of mechanical components cycling through their maintenance routines. If the ship rotates to generate artificial gravity, the rotation would introduce a persistent Coriolis effect that the inner ear never fully adapts to. Objects released from the hand would curve slightly before landing. Walking in one direction would feel marginally different from walking in the other. The body would register these discrepancies as a background wrongness that no amount of habituation entirely eliminates. If the ship does not rotate, the crew lives in microgravity for the duration, with all of its attendant physiological consequences: bone density losses that accelerate despite exercise countermeasures, muscle atrophy, requiring hours of daily resistance training simply to maintain function, fluid redistribution toward the head that creates chronic pressure sensations, and progressive vision impairment as intraocular pressure rises. Either option produces a physical environment that the human body can tolerate for months, but that corrodes health and comfort across years. The biological environment would be equally stripped of richness. No animals beyond whatever minimal fauna the life support ecology requires. No birdsong drifting through an open window. No insects moving through afternoon light. No sound of water moving over a natural surface. No body of water large enough to swim in or even to sit beside and watch. The food, however carefully cultivated in onboard hydroponic systems, would lack the variety that a planetary ecosystem provides across seasons and geographies. No fish pulled from open water, no fruit from an orchard, no bread from a bakery 2 streets away. The menu would cycle through whatever the production modules could sustain, and over years, the repetition would flatten eating from a source of pleasure and social ritual into something closer to a mechanical refueling process. These deprivations sound modest, considered individually. No person dies from the absence of birdsong, but sensory richness is not a luxury that human well-being happens to enjoy. It is a substrate on which human cognition operates. The brain requires varied, unpredictable input to maintain the flexibility, creativity, alertness, and emotional regulation that healthy function depends on. Studies of controlled sensory deprivation demonstrate measurable cognitive decline within days of its onset. Reduced, sustained attention, impaired problem-solving, increased susceptibility to perceptual distortion, emotional instability that compounds under continued exposure. An interstellar mission does not impose total sensory deprivation, but it imposes a degree of sensory monotony so complete, so unrelenting, so utterly without variation or novelty across years and decades that its cumulative effects have no true precedent in any documented human experience. Human beings are not built for this. The cognitive and emotional architecture that evolution produced operates on the assumption of environmental richness, social complexity, natural cycles of light and season, and the constant low-level novelty that a living world provides. Strip all of that away. Seal a person inside a manufactured environment for years, with no variation beyond what human ingenuity can artificially introduce, and the psychological consequences are severe and thoroughly documented across every analogous setting humanity has created. Submarine crews, Antarctic winter over personnel, and long-duration station residents all describe recognizable versions of the same syndrome. Irritability that builds without obvious cause, a progressive dulling of cognitive engagement, emotional flatness that makes previously meaningful activities feel hollow, social withdrawal from people who were once close, disrupted sleep that never fully normalizes regardless of how carefully the light cycle is managed, and a pervasive erosion of the sense that daily effort carries meaning, a condition that researchers studying extended confinement have described as the third quarter phenomenon. The third quarter phenomenon refers to the motivational collapse that tends to occur when a confined group passes roughly 3/4 of the way through a defined period of isolation. The end is visible but not yet close. The beginning is far enough behind that the energy and novelty of departure have fully dissipated. The middle has been endured for so long that endurance itself begins to feel like the only remaining purpose. In studies of Antarctic expeditions, submarine deployments, and spaceflight simulations, this phase is consistently marked by the sharpest declines in morale, the highest rates of interpersonal conflict, and the most significant drops in cognitive performance. On a mission of fixed and known duration, the third quarter eventually passes, and arrival approaches to rekindle motivation. On an interstellar mission lasting decades, the third quarter phenomenon would not be a phase to survive. It would be a recurring condition, cresting and subsiding in waves across the interminable middle passage of a journey, measured not in months but in generations. Interpersonal dynamics compound the problem with a particular cruelty. Small groups confined together for extended periods develop friction with something close to statistical certainty. Personality clashes emerge. Power dynamics calcify into patterns that become impossible to escape. Romantic entanglements complicate professional relationships in ways that closed environments intensify rather than resolve. Grudges accumulate. Communication patterns break down. These phenomena appear in every long-duration confinement study ever conducted, without exception. On a submarine, a deployment lasts months and the crew rotates afterward. On an interstellar vessel, the crew is permanent. There is no reassignment, no transfer request, no shore leave to discharge, accumulated tension and return with a measure of psychological renewal. If two crew members develop an irreconcilable conflict, they must continue living and working within meters of each other for the remainder of their lives. If a leader becomes psychologically unstable, or authoritarian, or simply wrong in some consequential way, there is no external authority capable of intervening. The ship's social order must be self-correcting, because nothing outside it can correct it. The psychological burden extends to something more fundamental than discomfort or friction. It reaches into the question of meaning itself. Exploration has always derived its motivating power from the promise of return. Explorers depart, endure, discover, and come back to share what they found. The return is what converts suffering into story, distance into knowledge, hardship into something the civilization left behind can learn from and build upon. A crew bound for Proxima Centauri may never return. Even if the technology to make the outbound journey exists, the return voyage doubles the time. A 40-year outbound crossing becomes an 80-year round trip. The crew members who departed as young adults would arrive back on Earth, if they survived at all, as elderly survivors in a world that had moved decades beyond anything they remember. More likely, the mission is one way. The crew departs knowing they will never see Earth again, knowing their families will age and die, while time-delayed signals crawl across the void, knowing that the planet they carry in their memories will not resemble the planet that exists by the time their messages arrive there. They are not explorers in any traditional sense of the word. They are emigrants. They are exiles. And the psychological weight of voluntary, permanent, Irrevocable exile from everything a person has ever known is a burden that no selection process, no training regimen, and no onboard counseling system has ever been designed to manage, because no human being has ever been asked to carry it. Now, push the problem further, because everything described so far applies to the founding crew, the people who chose to board the ship, but a journey lasting 80 or 100 years cannot be completed by the people who began it. The founding generation will die in transit. Their children must carry the mission forward, and those children did not choose. This is the generation ship concept, and it represents the only crewed interstellar architecture that does not require propulsion performance bordering on the physically impossible. If the crossing cannot be made fast enough for a single crew to survive it, the vessel must be large enough and self-sufficient enough to sustain a reproducing human population across multiple successive generations. The ship becomes not a vehicle but a habitat, a world, a sealed civilization aimed at a point of light across the void, populated across the centuries by people who were born inside it, who will live their entire lives inside it, and who will die inside it, passing forward a mission that was chosen for them by ancestors they will never meet. The ethical weight of this is staggering in a way that engineering specifications cannot address. The founding generation boarded voluntarily. They understood the commitment they were making, however imperfectly. They accepted the sacrifice with open eyes. But their children do not choose. Their grandchildren do not choose. Every subsequent generation inherits a destiny imposed by people who are already gone, decided upon in a world none of the inheritors ever saw or touched or breathed the air of. These descendants are born into confinement. They grow up understanding that the walls surrounding them are the walls of a vessel in transit, that the sky is a concept stored in databases and described in recordings made by people long dead, that the earth their ancestors departed from is a place they will never visit, never stand on, never know, through anything other than inherited description. Their entire existence, from birth to education to work to reproduction to aging to death, is defined by a journey they did not initiate, aimed at a destination they have only been told about, justified by a purpose they must accept on faith. Because no one alive aboard the ship has any direct experience of either the world that launched the mission or the world toward which it travels. Consider what daily life actually consists of for a person born in the 4th generation of a 10-generation crossing. This person has never seen Earth. Their grandparents never saw Earth. The founding generation exists only as names in historical archives, as faces in recordings, as voices explaining a decision made more than a century before this person drew their first breath. The destination, Proxima Centauri, remains 6 generations distant. It is not a place this person will ever reach. It is not a place anyone they know will ever reach. The complete arc of their life, everything they will ever experience, will unfold inside the same vessel. Their professional purpose will consist of maintaining systems that keep the ship functional for a crossing whose completion they will never witness. Their social world will consist of the same few hundred or few thousand people they have known since childhood and will know until they die. Their children will be born into the same world and face the same constraints without modification. The journey is not a temporary condition that defines one period of their existence. It is the totality of their existence. They are not travelers. They are inhabitants of a machine whose sole function is to keep moving through a void that none of them chose to enter. What motivates such a person to maintain the vessel's systems, to raise children who will maintain it after them, to preserve the knowledge and the capability that will only matter 6 generations? Hence, when people none of them will ever know finally arrive at a destination none of them will see. These are not engineering questions, and they cannot be resolved by engineering answers. They are questions about the limits of inherited purpose, about whether human beings can sustain meaningful commitment to a goal they will never see achieved, about whether meaning itself can survive transmission across centuries of sealed, motionless confinement without transforming into something that no longer resembles the original intention. No human society has ever tested these questions under conditions of complete isolation and permanent enclosure. The historical record that does exist offers limited comfort. Isolated communities cut off from broader contact undergo cultural drift within remarkably few generations. Island populations develop distinct languages and belief systems that diverge rapidly from their origins. Religious communities that seal themselves from outside influence produce doctrines that bear diminishing resemblance to their founding principles within a century or two. A generation ship would represent the most isolated human community in the history of the species. Sealed inside a metal hull, with no contact beyond time-delayed signals from an Earth growing more alien with every passing year. The culture aboard after 10 generations might be unrecognizable compared to the culture that built and launched the vessel. The mission's original purpose might have been reinterpreted, questioned, reimagined, or forgotten entirely. The technical knowledge required to operate the ship's systems might have degraded as educational priorities shifted imperceptibly across the generations. The skills necessary to land, establish a settlement, and survive on an alien world might have atrophied during centuries of transit when those skills had no practical application and no lived context to make them feel real. No human institution has survived intact across the timescales a generation ship demands. The Roman Empire in its various configurations, the papacy, certain Chinese imperial dynasties, each lasted at most a few centuries before transforming beyond recognition or collapsing entirely. A generation ship must maintain not merely mechanical function but social coherence, shared purpose, and knowledge continuity across periods that exceed the lifespan of every civilization in recorded history. The ship's governance structure must survive leadership transitions, ideological evolution, resource disputes, and the inevitable drift of values across generations. Sealed inside a vessel with no external pressure to enforce cooperation, no outside threat to unify against, and no frontier to expand into. The only frontier is arrival. And for most of the journey, arrival is an abstraction too remote and too impersonal to motivate the daily sacrifices that keeping a complex machine alive requires. History suggests what happens to communities that lose contact with the wider world. They change in ways their founders could not have predicted and would not have chosen. They become something new, sometimes something remarkable, sometimes something that has entirely forgotten why it exists. A generation ship crossing the void to Proxima Centauri would be subject to the same forces of cultural transformation that have reshaped every human community across every span of time, but without any of the external pressures and exchanges that normally moderate and redirect that transformation. Sealed inside the hull, the community drifts in whatever direction its internal dynamics carry it, with no correction possible from outside, and consequences for certain kinds of drift that are not merely unfortunate but terminal. Social collapse aboard a generation ship is not a political failure. It is not a cultural setback. It is an extinction event. Each of these challenges, the communication delay measured in years, the physical impossibility of rescue, the relentless radiation bombardment, the mechanical fragility of systems asked to operate beyond any demonstrated endurance, the psychological degradation of minds sealed inside manufactured environments across lifetimes, is independently severe enough to threaten any interstellar mission ever conceived. Taken one at a time, each represents a problem at or beyond the current frontier of human engineering and human understanding of ourselves. But they do not occur one at a time. They occur simultaneously, compounding one another in ways that multiply the total risk far beyond any simple sum of the individual threats. Consider how failure cascades in practice. A galactic cosmic ray heavy ion event damages a circuit board buried inside the atmospheric processing system. The system does not fail immediately or dramatically. It begins producing slightly elevated carbon dioxide concentrations in the habitat air, not enough to trigger any automated alarm, enough to cause persistent headaches, mildly impaired concentration, and fragmented sleep across the crew over the following weeks. The crew, already experiencing the cognitive dulling that accumulates through years of long-duration confinement, does not identify the source of the problem quickly. The symptoms are subtle. They resemble fatigue, They resemble the ordinary psychological wear of the journey. By the time the fault is traced to its origin, the degraded air quality has been affecting decision-making and reaction times aboard the ship for months. The repair requires a component that was manufactured on Earth and cannot be perfectly replicated using the onboard fabrication equipment available. The crew improvises a functional workaround using materials cannibalized from a backup system designed for a different purpose. The workaround holds, but it permanently reduces the backup system's capacity to respond to its own future failure. The margin narrows. The next failure begins from a weaker starting position. Or, consider a different sequence. A dust grain traveling at relativistic velocity penetrates the outermost layer of hull shielding and damages a coolant line in the thermal regulation system. The leak is slow. The pressure drop is gradual enough that automated monitoring flags it as a low-priority anomaly rather than an immediate emergency. But thermal management in one section of the habitat begins to drift. Temperatures fluctuate in ways that affect the food production module adjacent to the damaged line. The crew relocates operations from the affected section, compressing daily activity into a smaller portion of the available habitat volume. The increased physical proximity intensifies interpersonal friction that has been building quietly for years between two crew members whose professional relationship has never fully recovered from an unresolved conflict earlier in the journey. The friction escalates during the repair operation, delaying the work by days. The thermal imbalance damages a crop cycle in the food production module before the repair is completed. The food supply tightens. Rationing begins at a modest level. Morale drops across the entire crew. The next system anomaly occurs in an environment where the people responsible for addressing it are already fatigued, underfed, crowded, and carrying unresolved interpersonal tension. No single event in either of these sequences is catastrophic in isolation. Each is manageable if it occurs alone, in a fresh environment, with full resources and a rested crew, but they do not occur alone. They occur in sequence and in combination, each degradation altering the conditions under which the next challenge must be faced, each repair consuming resources that cannot be replenished, each interpersonal fracture widening under sustained pressure with no relief possible from outside. This compounding behavior is not speculation. It is the documented characteristic of complex systems operating under sustained stress without external resupply or maintenance. It is precisely why submarines rotate their crews after months rather than years. Why Antarctic stations receive resupply flights even during the harshest winter conditions. Why the International Space Station receives cargo missions on a schedule measured in weeks rather than years. Every long-duration human operation in a hostile environment has learned through direct and sometimes costly experience that isolated systems degrade, that degradation accelerates under stress, and that the acceleration compounds across interdependent subsystems in ways that are difficult to model in advance and impossible to stop once momentum builds. A crewed interstellar vessel would be the first human habitat ever asked to operate under these compounding pressures for decades without any external input of any kind. Not a resupply, not a replacement component, not a fresh crew member bringing new skills and new perspective. Not a single molecule from outside the hull. The margin for error is not thin. It is a knife edge that must be maintained continuously across a time span longer than most nations on Earth have survived in any recognizable form. The void between stars is not merely empty space. It is an environment of layered, compounding hostility, where distance, time, radiation, particle impact, mechanical entropy, and psychological erosion converge into a sustained assault on every requirement a crewed mission must satisfy to remain viable. The journey to Proxima Centauri does not merely test technology. It tests the entire concept of human self-sufficiency in a setting where self-sufficiency is the only available option and where the margin between survival and failure is measured in decisions made by exhausted people in a sealed container that grows more worn with every passing year. Now consider the one phenomenon that appears, at first encounter, to offer escape from the most brutal aspect of the journey, the dimension of time itself. Albert Einstein's special theory of relativity, first published in 1905, and confirmed by more than a century of experimental evidence across every scale and context in which it has been tested, predicts that time does not pass at the same rate for all observers. Specifically, it passes more slowly for objects moving at significant fractions of the speed of light, relative to a stationary frame of reference. This is not an illusion produced by the motion. It is not an artifact of measurement or perception. It is a fundamental property of space-time itself, as real and as physically consequential as gravity. A clock aboard a spacecraft, traveling at high velocity, genuinely ticks more slowly than a clock on Earth. The crew genuinely ages less than the people they left behind. At 50% of the speed of light, the effect is modest. Time aboard the ship passes at roughly 87% of the rate on Earth. A journey that takes 8.48 years, as measured by observers on Earth, would be experienced by the crew as approximately 7.3 years of subjective time, noticeable across a long mission, not transformative. The crew still ages through most of a decade. The journey still consumes the better part of a human life stage. At 90% of the speed of light, the dilation becomes genuinely dramatic. Time aboard the ship passes at roughly 44% of the Earth rate. The crew would experience the 4.24 light-year crossing in approximately 2 years of shipboard time, while roughly 4.7 years elapsed on Earth. At 99% of the speed of light, the dilation factor reaches approximately 7. The crew would experience the journey in roughly 7 months of subjective time, while over 4 years passed on Earth. These numbers appear, on first reading, to change everything. If a crewed vessel could be accelerated to 90% of the speed of light, the crew would arrive at Proxima Centauri, having aged only about 2 years. The journey would be shorter than many submarine deployments. The psychological burden would be manageable. The mechanical endurance requirements would be modest. Time dilation seems to dissolve the cruelest aspects of interstellar travel in a single elegant result drawn from the structure of the universe itself. But the elegance conceals something devastating. The energy required to accelerate a crewed vessel to 90% of the speed of light is not merely large. It is large in a way that belongs to a different category of physical quantity from anything human civilization has ever produced or seriously contemplated producing. As an object with mass approaches the speed of light, the energy required for each additional increment of velocity increases without limit. The relationship is not linear, it is asymptotic. Reaching 90% of light speed requires accelerating the ship's rest mass to a kinetic energy roughly equal to its total mass energy equivalent multiplied by a factor of approximately 1.3. For a vessel massing 1,000 metric tons, a modest figure for a crewed interstellar ship, the kinetic energy at 90% of light speed would be approximately 1.17 times 10 to the 23rd joules. That figure is roughly equivalent to the total energy consumed by human civilization across 200 years, compressed into the kinetic state of a single vessel, for one ship, one departure, one crossing. The energy budget is not beyond current technology in the way that fusion propulsion is beyond current technology, meaning achievable in principle with sufficient development. It is beyond any energy source humanity has ever seriously proposed for spaceflight. Even antimatter annihilation, the most energy-dense fuel that known physics permits, would require hundreds of metric tons of antimatter to accelerate and then decelerate a crewed vessel at these velocities. Humanity currently produces antimatter in quantities measured in nanograms per year, at costs estimated in the trillions of dollars per gram. The gap between what exists and what relativistic crewed flight requires is not a gap of engineering. It is a gap of physical scale that no plausible roadmap of technological development closes within any foreseeable time frame. At the velocities humanity might actually achieve with advanced but physically grounded propulsion systems, 10 to 20% of the speed of light, time dilation is present but operationally negligible. At 10% of light speed, time aboard the ship passes at roughly 99.5% of the rate on Earth. The crew saves less than 6 months across a 42-year journey. The dilation is real, mathematically confirmed, and entirely irrelevant to any human experience of the voyage. The journey still takes decades, the crew still ages through the crossing, the generations still turn over if the mission extends long enough. Time dilation offers genuine relief only at velocities that require energy budgets indistinguishable from fantasy. It helps only where it cannot be reached. At the speeds that remain physically achievable with any technology grounded in known science, it is a rounding error measured against a sentence of decades. And even in the hypothetical scenario where relativistic velocities could somehow be achieved, time dilation does not solve the problem of separation from Earth's timeline. It reshapes that problem into something stranger, and in some ways more disturbing. It does not eliminate the time that passes on Earth during the crossing. It only compresses the time the crew experiences aboard the ship. A crew that subjectively experiences 2 years of travel at 90% of light speed arrives at Proxima Centauri to find that nearly 5 years have elapsed on Earth since their departure. If they complete the return journey at the same velocity, they arrive home to a planet that has aged approximately a decade in their absence, while they themselves have aged only about 4 years. The displacement sounds manageable for a single crossing to the nearest star, but it scales with distance in ways that become progressively more disorienting. A round trip to a star 20 light-years away at 90% of light speed produces a temporal displacement of nearly 45 years on Earth, against roughly 19 years of subjective crew time. The travelers return biologically middle-aged to find a world that has moved nearly half a century beyond the moment they left. Friends have retired or died. Children have grown into middle age themselves. The social and political landscape has shifted in ways that no amount of time-delayed correspondence could have prepared the returnees to navigate. The crew members are not merely changed by their experience. They have become temporal refugees, displaced not in space but in time, arriving in a present that belongs to people they have never met, and a world that has reorganized itself entirely in their absence. At more extreme velocities, the displacement becomes grotesque in its scale. A traveler departing at age 30 for a star 40 light-years away at 99% of light speed returns at roughly age 41. On Earth, more than 80 years have passed. Every person the traveler knew at departure has died. The institutions that trained and launched the mission have been dissolved, rebuilt, and in some cases dissolved again. The language has drifted. The borders on political maps no longer match the ones memorized before departure. The technologies are unrecognizable. The traveler steps off the ship biologically young and finds themselves an artifact, a curiosity from a previous era, a living fossil of a world that the people around them know only from historical records. The homecoming is not a reunion. It is an arrival in a civilization that has moved so far beyond the one that launched the mission that the returning traveler has no more natural place in it than a person from the 19th century would have in the present day. The stars were reached, the crossing was made, and the cost was membership in the human timeline itself. Time dilation does not conquer time, it redirects its cruelty. It allows the body to survive the journey, while stripping away the temporal context that makes survival meaningful. The crew arrives, but the world they arrived from no longer exists in the form they carried in their memory, and the world they arrived to has no particular place waiting for them. This is the temporal dimension of interstellar travel that no engineering solution can address, because it is not an engineering problem. It is a consequence of the speed of light, the distances between stars, and the structure of space-time itself. The journey to Proxima Centauri, regardless of how it is conducted, severs the travelers from their own time. At slow speeds, the separation is generational. The founders die in transit, and their descendants arrive as strangers to both worlds, the Earth they never knew and the Proxima system they were born toward. At fast speeds, the separation is relativistic. The crew arrives biologically intact, but temporally displaced, out of synchronization with the civilization that built and launched the vessel. At any speed, the journey creates a rupture between the travelers and the human timeline they departed from. They do not merely leave Earth, they leave the present, and the present, unlike a physical location, cannot be returned to. This rupture is the deepest source of what makes the journey to Proxima Centauri something beyond a physical challenge. Not the distance, not the velocity requirements, not the radiation or the dust, or the mechanical entropy, or the psychological monotony. Those are problems that can, in principle, be approached through engineering, given sufficient technology, sufficient resources, sufficient ingenuity applied over sufficient time. The temporal rupture cannot be engineered around. It is a consequence of how the universe is structured, a consequence of the fact that light moves at a finite speed, that stars are separated by distances that light requires years to cross, and that human beings are embedded in time in a way that makes their connection to a particular present moment as fundamental to their identity as their connection to a particular place. No propulsion system can make the journey instantaneous. No communication technology can make a conversation across 4.24 light-years feel like a phone call. The speed of light is not a barrier waiting for a sufficiently clever engineer to find a way around it. It is a law of physics as foundational as the conservation of energy, as the increase of entropy, as the simple fact that matter occupies space. It defines the structure of the universe. And what it defines at interstellar distances is separation. Permanent, irreversible, structural separation between the travelers and everything they leave behind. This is the full weight of what the title means. The terrifying journey to Proxima Centauri is not terrifying because Proxima Centauri is exotic or menacing or shrouded in mystery. The star itself is a dim, quiet red dwarf with a small retinue of battered worlds sitting at the edge of a triple star system in an unremarkable corner of the Milky Way. The terrifying element is precisely that this is the nearest star, the closest conceivable interstellar destination, the least extreme version of the problem, the minimum case. The gentlest possible introduction to what it would mean to leave the solar system, and even this minimum case demands a journey so prolonged, so isolated, so severed from Earth and from the human timeline, that it ceases to resemble exploration in any sense the word has ever carried, and begins to resemble something for which no word yet exists. Every previous act of exploration in the full span of human history maintained some thread of continuity between the explorer and the civilization that produced them. Columbus sailed west and returned east. Magellan's expedition encircled the globe and came home, or most of it did. The Apollo astronauts walked on the moon and were back on Earth within a week. Even the most extreme polar expeditions, the most dangerous mountaineering ascents, the deepest ocean dives ever attempted, preserved some functional connection between the person who went and the world they departed from. The departure was temporary, the distance was reversible, the time away was bounded by a known return. An interstellar journey breaks every one of those threads simultaneously. The departure is permanent or effectively so. The distance is reversible only at costs measured in decades or lifetimes. The time away is so vast that the world the travelers remembered at departure will not be the world that exists when their messages arrive, let alone when they might conceivably return. The journey does not extend human reach outward from a stable center. It severs the traveler from that center entirely. They become something new, not explorers in any previously understood sense, not colonists, at least not in any sense that would be recognized by the people who used that word before them. They become the first humans to exist genuinely outside the temporal and spatial framework that has contained every human life ever lived on this planet. They carry their humanity with them into the void, but the connections that gave that humanity its context, its meaning, its place in the larger story of the species, those connections do not survive the crossing intact. And this is the nearest star. This is the easiest version. This is the shortest crossing the galaxy has to offer. The Milky Way contains roughly 400 billion stars. The nearest few dozen sit within 20 light-years. The nearest few thousand within 100. The galaxy itself extends across more than 100,000 light-years of space. The journey to Proxima Centauri is not the bottom rung of a ladder that humanity might climb star by star toward a galactic civilization. It is a demonstration that the ladder itself may not exist in any form compatible with human life as we currently understand it. That the distances between stars are not engineering challenges to be progressively overcome, but structural features of the universe that impose costs on any crossing that may simply exceed what human beings are capable of paying. Not in money, not in engineering hours, in time, in connection, in the continuity between who you are when you leave and who or what you become when you arrive. The universe does not forbid the crossing. Physics permits it. Objects can travel between stars. Voyager 1 is doing exactly that right now, silently, at 38,000 miles per hour, carrying a golden record engraved with sounds and images from a world it will never see again. But the universe prices the crossing at a rate that may be beyond what human beings can pay, without surrendering the very things that make the crossing worth attempting. The cost of reaching the nearest star is not measured in fuel or fabrication hours or mission budget. It is measured in the surrender of everything that ties the travelers to the world that built the ship, to the time in which that world exists, and to the species that dreamed of the stars in the first place. Proxima Centauri sits 4.24 light-years away, a dim red dwarf orbited by a handful of small, radiation-scoured worlds, one of which might, under certain conditions, hold liquid water somewhere on its surface. It is the nearest star, the closest destination beyond our solar system, the most accessible point in the entire galaxy, the minimum distance, the best case. And reaching it would require a journey so extreme in duration, so absolute in its isolation, so complete in its severance from Earth, from civilization, from the present moment, that the people who undertook it would no longer be travelers in any sense that word has ever held for our species. They would be something else, pioneers without precedent, exiles who chose their exile with full knowledge of what they were surrendering, human beings who departed the human world not because the destination demanded it, but because the space between here and there demanded it, because the void demanded it, because 4.24 light-years of nothing, the shortest interstellar distance in the sky, is already enough to transform a journey into a departure, exploration into exile, and the ancient promise of the stars into a burden so profound that the nearest one, the very nearest, already sits at the far edge of what humanity was built to bear. The stars are visible every clear night from anywhere on Earth, not washed out by city light. They have always been visible. They have always appeared close, scattered across the dark like embers from a fire, near enough to name, near enough to navigate by, near enough that humans have spent 10,000 years telling stories about them. And the nearest one, the very nearest point of light beyond our own sun, is already impossibly, terrifyingly, and in its own strange way, beautifully far. It will still be burning long after we are gone, long after this planet has been silenced, long after the last question about it has been asked by anyone capable of asking. Patient, dim, unreachable, waiting at a distance that has no name in any language evolved to describe a world the size of this one. It is right there. It has always been right there. And that, in the end, is the most terrifying thing of all.